Is the moon getting smaller and moving away? What should we name Planet 9? And is there any way to recycle space junk? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers, as always, wherever you are across my channel. If a question pops into your brain, just write it down. I will gather them up and I will answer them here. All right, let's get into the show. Tink. Would they ever make a mini James Webb that's about the size of a phone and send it out past Neptune and point it back towards Earth to see what our signature is so we know what to look for? That's an amazing question. And no, they will never make a teeny tiny telescope and send it far out into the solar system to look back at Earth and then try to get a sense of what our planet looks like. There are easier ways to do that, and that is that you can simulate it. You can take the capability of a telescope like Webb or some mission or spacecraft, and you can understand planet Earth, shrink it down, and start to understand and simulate whether or not current telescopes have the capability to be able to view them. And this work is done a lot. We've reported on this quite a bit, where astronomers have taken the capabilities of some telescope like Webb, and they've said, could we detect the presence of chlorofluorocarbons in the atmosphere of Earth? And then they run the numbers, and it turns out that yes, that if Webb was within a certain distance of Earth, it could actually detect the presence of human technology in our atmosphere, which is pretty amazing. And there's like a very famous example of this when the Galileo spacecraft was launched to Jupiter. It had to make a flyby of Earth for a gravitational assist. And so it came past Earth, and Carl Sagan at the time, when he was still alive, said, this is the perfect example. Could we use a spacecraft, pretend that it's flying past some other planet? Would it be able to detect the presence of life? Would it know that there's people here, that there's life forms here? And, based on the observations that Galileo made of Earth, his opinion was yes, that you could detect the presence of the oxygen in the atmosphere and the ozone and various other images and chemicals and things that would give you that sense. I wouldn't be so sure now. I think what we know now is that, in fact, trying to puzzle out biosignatures is a lot more complicated than we simplistically believed 30 years ago. But still, it's a neat prospect. And so, yeah, this idea of Earth as an analog for an extrasolar planet is done all the time. And in fact, you have other examples too, like where Venus is an analog for an exoplanet. So, Venus is right next door, and yet it is extremely different to Earth, both in terms of its chemistry of the atmosphere, the temperature, the pressure, but the planet is like the same size and roughly the same mass and has roughly the same surface gravity and roughly the same composition. And so we got this world that's very, very different. And so when you look at some exoplanetary system, can you distinguish between an exo-Venus and an exo-Earth? And in fact, one of the new attempts made by James Webb in observing the TRAPPIST-1 system, they were observing the first two planets in the system, and they were asking themselves, can we distinguish between, can we see an atmosphere around this planet? They were hoping that they would see some kind of super Venus, but they didn't. They were like super Mercuries. So, but yeah, this is often simulations are run, Earth as an analog, see what you could learn with whatever telescope, use that as a baseline, and then go from there. I'm sure you noticed the Star Trek planet name that appeared above my shoulder, and this is a way for you to vote, for you to tell us what you thought was the best question, best answer combo of the week. So you're going to see a different Star Trek planet name appear above my shoulder. And so just watch to the end of the show and then just put in the comments down below which you thought was the best. Now, we put the names of all of them in the time codes, in the timeline. It should be easy for you to be able to watch. You can sort of, after you finish the episode, you can go find the one you liked and put it into the comments down below. And the winner last week was Aeturen. Why are we wasting time and money on Mars? And I hope you all enjoyed the question and my answer. All right, so don't forget to vote. Corvair Wind. Will we ever build a satellite to explore the areas where Planet X or the equivalent would be orbiting? So Planet 9 is this hypothetical planet that astronomers have been searching for. They haven't seen it directly, but they've detected its presence through the gravitational influence of all the different Kuiper belt objects that are out in that region. And this process of discovering a planet based on the gravitational interactions, this was done before. This is how astronomers found Neptune. They looked at the motions of other planets. They calculated that they should find a giant planet in this part of the sky, and lo and behold, they did. And so Mike Brown, Konstantin Batygin, and other researchers have examined the movements of tons and tons of Kuiper belt objects, and you could only get these sort of resonances out in the Kuiper belt if there was some large object moving around in that area. But space is big, it's vast, and so to search every part of the sky requires a very powerful telescope that's able to do that kind of work. Like, if astronomers knew exactly where to point James Webb, they could see Planet 9, even if it was really dim, really faint. Like, think about it. They found Saturn and Jupiter-sized rogue planets in the Orion Nebula, which is like over 1,000 light years away. So Webb can see this kind of thing, can see very small objects, but it is this tiny little field of view. And so you have to know where to point to know what it is that you're going to be looking at. So now you're asking, like, could you build a satellite to explore the areas? Well, the problem is that region is gigantic. Like, objects are within, I forget the number, but it is like they are within hundreds of thousands of kilometers, no, millions of kilometers of each other, like on average. Like, think about, say, the distance from the Earth to the moon. That is, objects in the Kuiper belt are dramatically farther away from each other than the distance from the Earth to the moon. And so to have something that's able to find objects out in that region, it's just too big a space to search for. It takes hundreds of years for Pluto to orbit once around the sun. And so you would need a fleet of spacecraft every maybe thousands of spacecraft to try and survey the area. And so in fact, the best way to search for Planet 9, even though it's really far away, is to use a really powerful telescope here on Earth that is observing a big chunk of the sky, and it's watching for anything that's going to be moving through the field of view. And that telescope is Vera Rubin, which is going to be coming online later this year. And it is going to be doing exactly that, watching the entire southern sky, taking new pictures every 3 nights, and trying to find anything that moves. And one of those things has got to be Planet 9. If Vera Rubin doesn't see Planet 9, then it doesn't exist. That's like how powerful this telescope is. So we're like a year away from somebody announcing the discovery of Planet 9 at this point. Ted Krause, is our moon actually getting smaller in size and moving away? Yes and yes. So actually, there was one part of this is fairly well known, has been discussed for a long time. And another part of this is pretty brand new research that came out in the last couple of weeks. So is the moon moving farther away? And the answer is yes. And we know that the moon is drifting away from the Earth a couple of centimeters every year, 1 centimeter every year. And that is due to the interaction between the moon and the Earth. So the moon is tidally locked to the Earth. So the moon only shows one face to the Earth, but the Earth is not tidally locked to the moon. And so the Earth turns, and within 24 hours, while the moon is slowly orbiting around us. But the Earth is trying to tidally lock to the moon. It's going to take 50 billion years, but finally, when that happens, you'll have the Earth pointing directly at the moon. But what happens is that the moon's gravity is pulling on the Earth. The Earth, it sort of squishes the Earth, and it gives it these little handles on either side of the Earth. And then each time that the Earth turns, the moon is sort of pulling on one of those handles one way, pulling on the other way, and it's trying to slow down the Earth's rotation each time. And eventually, like I said, after 50 billion years or so, it'll finally have completely slowed the Earth down. And so a day length on Earth is getting longer and longer. But when you consider the Earth and the moon together, you have to account for the entire angular momentum between the two objects. There's a conservation of momentum. And so the price that the moon pays for slowing the Earth down is that it drifts away from us a couple of centimeters a year. And so slowly over time, eventually it'll reach this perfect spot where the moon only shows one face to the Earth only shows one face to the moon. They are no longer, the moon is no longer drifting away from us. So that's half the story. And then the other part is it is actually getting smaller in size. And the answer is yes, but this is brand new research. And so astronomers noticed a bunch of landslides that were happening near the moon's south pole and really across the entire moon. And what's happening is that you get these moonquakes that are causing shaking and shifting on the moon. And they were able to determine that this is coming from the fact that the moon is still kind of cooling down. Even though it seems solid on the surface, it probably has some level of a molten core deep down inside. And as it cools down, it shrinks. And so its surface kind of crunches and crumbles. And this causes places that were maybe not too steep before. Now they're a little bit steeper. And then when you get this slight moonquake, you can get these landslides. And so the consequence of this is that there's a bunch of regions near the moon's south pole that researchers have looked at and said, here's a bunch of spots that could have landslides while there are astronauts on the surface of the moon. And this is caused by the moon shrinking, and you're getting these additional landslide dangers. And one of these could wipe out a base on the moon. And so they've mapped out all these spots, and they said, like, here are all the debris fields that you want to avoid when you're setting up on the moon. So yeah, moon is moving away and it's getting smaller. Rich Higgins. Hey Fraser, what are your plans for the April eclipse? My plans right now are to go to Texas. So we've got family in Texas and pretty close to the eclipse path. So hopefully we can just hang out in our backyard and watch as the eclipse goes overhead. But for those of you who are planning to go to the eclipse, it's important to stay mobile. And so I say that kind of roughly, like I might be in Texas, probably in the Dallas area, but I could be hundreds of miles north or south, depending on what the weather is going to do. So if you're planning to go see the eclipse, then you need to choose a place where you think it has the highest chance of having sunshine. And Texas is a pretty good shot for that. You know, it's going to pass into Canada. I don't know, like Canada in April, I'm not sure I like your chances. So Texas is good, but on the day or leading a few days up to the eclipse, you got to be watching the weather forecast. And then you got to say, okay, it looks like there's going to be better weather a state to the north or a state to the south. And then you've got to drive and get yourself set up closer to where you're going to have that good weather. And even on the day of the eclipse or just before the eclipse, you got to check the weather. You got to find out where the good weather is going to be. And you got to be ready, even down to the last couple of minutes, to be willing to run or drive or bicycle to a place that gets you a better view of the eclipse. On the 2017 eclipse, I was trapped in a football stadium and I wasn't able to do that. And if I could have driven just 1 kilometer in any direction, I would have gotten out from this giant cloud that was directly between me and the eclipse. And I only saw like the last 5 seconds of the eclipse. So yeah, I'm going to probably be in Texas. I might have something to announce exactly where I'm going to be in Texas, but stay tuned for that. Hourglass Sand. If two gravitational waves meet and crest high enough, will it poke a hole in space-time, looking like a vibrating black hole in and out of existence? So there's kind of two parts to this question. The first one is, can gravitational waves cause interference like electromagnetic waves, like water waves? And the answer is yes, that if you have 4 black holes colliding into 2 pairs close to each other and they're generating gravitational waves, you could get an interference pattern between the gravitational waves. Will it poke a hole in space-time? No, you'll just get a more powerful gravitational wave effect at the point of the peak. You'll get a less gravitational wave effect at the point of the trough, and it will have to be a fairly tight area for you to get that interference pattern. But still, it would happen. Jenny Christopherson. Do photons experience time as they travel through the universe? I mean, what is a photon experience, right? Like, it's just a little bit of light. So it doesn't think a lot, doesn't really contemplate its nature, doesn't have a watch, doesn't have a wrist. But if it did have a wrist, if it did have a watch, no, a photon would not experience any time. And this is a predictable consequence of when you calculate the amount of time that it takes when you use general relativity. So when you calculate and you punch in the speed of light into the calculation, then you get the amount of time elapsed turning into 0. And so from the perspective of the photon, 0 time elapses. Photon is created, it travels any amount of distance, it could travel for 13.8 billion years, arrive at, be absorbed by your eyeballs, and from the photon's perspective, it experienced 0 time. And I know that's a head scratcher. Now, where that gets interesting for us is that as you want to travel at relativistic velocities, you want to get closer and closer to the speed of light, then the amount of time that you experience is getting closer and closer to 0. But it's always some time. You are experiencing the time. It's just that from the perspective of the rest of the universe, it looks like you're experiencing no time. And so you could travel for billions of light years at extremely close to the speed of light, and yet you wouldn't age more than a few decades. But you'd have to be extremely close to the speed of light. REM MSJ. What would be considered an unequivocal biosignature? This is a big problem, as we're getting to the point where astronomers finally have the tools and techniques to measure the atmospheres of other planets, like we saw with James Webb failing to measure the atmosphere of the TRAPPIST-1 system, but also finding methane and water vapor and carbon dioxide and carbon monoxide and sulfur dioxide and all these interesting chemicals in the atmospheres of other worlds. The hope is that it's going to be able to measure some kind of biosignature. Here on Earth, the amount of oxygen that's present in the atmosphere is due to life. Life is exhaling oxygen, plants and stuff, and then other life is inhaling it. You get other stuff like ozone and so on. And there's other trace elements. We've got methane in the atmosphere, that's due to life. You've got other, even more trace chemicals that are in the atmosphere, again, due to life. And so the naive view for the longest time was that you would just take a telescope, you would point it at a planet, you would detect the presence of oxygen, you go, done, we did it, we found life. But it turns out there are plenty of non-biological ways of producing oxygen. There are ways you could produce ozone, there's ways you could produce methane, that every single chemical that anyone has thought of that could be an output from life, people have also been able to imagine non-biological ways that same chemical could be produced. And when you think about the vast distances involved, think about the distance from here to planets at Alpha Centauri, light years away, in our lifetimes, you're never going to be able to do better than measuring the presence of the chemicals in the atmosphere of the planet. You're not going to be able to go there and show up and land on the surface and see if it has trees and so on. So this is what's going to make a really exciting time in astronomy, our ability to detect the presence of chemicals in the atmospheres of other worlds, into this really frustrating time, because you're going to hear all of these announcements of all these amazing chemicals that have been found, and you're going to hear some people tell you that's it, they did it, they found life, this is, and you're hearing the whispers right now. I've seen a ton of like videos and news articles, like scientists are saying they found life. They haven't. They found chemicals that are produced by life on Earth, but they may or may not be produced by life on some other world. And so now the entire astrobiological community is putting its heads together, and they are attempting to identify the kinds of chemicals that would be unequivocal. Like, these are the chemicals that if you see it, you know you found life. And the problem is they still just haven't found them. And so they're moving towards combinations of chemicals, that there are kinds of chemicals that interact with each other in a way that if you see those two chemicals together, then it's more likely to be something that's produced by life than some other thing. Like, I forget what it's like, water vapor and methane, I forget, carbon dioxide. Anyway, there's combinations. And chances are astrobiologists will eventually settle on some recipe of interacting chemicals that just can't be sustained by a non-biological way. The other option is to go with something that is evidence of a technological civilization. Like, there aren't many sources of chlorofluorocarbons or really complicated molecules like that produced by nature. I don't know, maybe there is some tree out there that is releasing chlorofluorocarbons, but I don't think so. And so if you find like the presence of those chemicals in the atmosphere of some other world, then you've got a better chance to say, okay, yeah, there is life there. Also, it's a technological civilization that is in the process of, I guess, destroying its ozone layers. And so we kind of know where they are in their development phase. But, and I talk about this a lot now, and I hope other people talk about this as well, but like, just prepare yourself. Be patient. This is all going to take a long time. If you want to support the work we do at Universe Today, consider joining our Patreon club. Your support lets us have a minimum of ads and no sponsorship messages. Patrons get no ads on universetoday.com for life. Want the extra parts of the live stream that aren't in this edited version? You can sign up for a special patron-only podcast feed, get the overtime segments, as well as other special behind-the-scenes episodes, including our monthly patron-only question show. Side note, it's like 2.5 hours long. We answered every single question that anyone asked us for the patrons. So you should definitely check that out. Thanks to everyone who has already subscribed, and welcome to the recent newcomers: Vince Genovese, Thomas Allen, Niels Schwarting, Steve Wilson, Corey Hernandez, Michael Middleton, Jeff Wilson, Jay Joyner, Marcel Boudreau, Chris Aikman, Lee Ende, that ER guy. Join the club at patreon.com/universe today. Church discography. What should we name Planet 9? If you ask someone like Alan Stern, that question is already answered. The name for Planet 9 is Pluto. I don't have a dog in this fight. I don't care whether or not Pluto is a planet. I would be perfectly fine if there was 100 planets in the solar system, or 12 or 8. I don't really care. Each one is cool on its own right. But what should we call it? I mean, traditionally, these things will get names from mythology, but is there like a really appropriate name for something that was like hidden from us for a long time, that it was suspected to be there, it required a lot of research? But tell me your recommendations in the chat down below. I'd love to hear what you think would be a great name for Planet 9. Luke Skywalker. How soon can we recycle space junk so we don't need to launch more raw materials? Any project in the works? Well, I need to distinguish this. So, like, are there any projects in the works to help rescue spacecraft, to help give them a longer lease on life so that they don't need to deorbit and contribute to the space junk problem? Yes, there are several missions that have been flown in the past. There are many in the works right now that the hope is that they will be able to fly up, attach to some existing satellite that maybe it's a perfectly functioning satellite, but it no longer has any propellant left for its thrusters. And so the spacecraft would bolt on to the satellite and then act like its thruster module. And so you could then take this perfectly functional satellite and give it another 20 years. But to actually recycle space junk would mean to catch space junk. And that's going to be really tricky because each piece of space junk is moving at, varying speeds, but around 25,000 kilometers per hour, which is, way faster than a bullet. And so in order to capture a piece of space junk that is going 25,000 kilometers per hour on its own orbit, you have to match its velocity. You have to build a mighty big rocket, and you have to chase down, you launch from Earth with your giant rocket, right? Or Falcon 9, whatever. You launch with the Falcon 9. There's like a tiny little spacecraft on top that's like a little grabber. And then you launch this giant rocket. It chases down a piece of space junk. It puts out, sure, the first stage can land, but now you've got the second stage. It's going to turn into space junk. Plus, maybe it's going to, hopefully the fairing comes down. It can be recycled, but maybe there's other parts and stuff for the spacecraft for it to be able to get itself into the proper orbits. You're generating space junk, and then you grab a satellite. Now, what are you going to do with it, right? Are you going to try and move it to another orbit? Well, then you're going to need more engines, more thrusters, more propellant, more stages. You're going to kick off more space junk, and you're going to move this thing to some other orbit. Are you going to try to take it to a place where you can actually add it to some big garbage pile in space, in orbit? Well, then you're going to need even more thrusters. Like, people think there's just like junk in space. You just grab it. But they're all moving on their own individual trajectories. They're going at enormous velocities. And so each one is a puzzle on its own. And there's really no way to efficiently go and grab them all. There have been proposals to grab a couple where you've got like one spacecraft that maybe has some net or a harpoon and it can try to take down a troublesome piece of space debris. But there's nothing that could take out large chunks of the debris that's out there. We're going to have to just wait for it to re-enter the Earth's atmosphere and burn up all on its own. Sirac of Vulcan. Fraser, do you find sci-fi less compelling than you did in the past the more we learn about the universe? No, not at all. I find science fiction totally compelling. Like when you read science fiction, or when I read science fiction, I turn off the part of my brain that is attempting to judge the realism of what it is that I'm reading. So if they've got a faster than light travel system, if they've got weapons that use black holes or whatever, I don't care. It's fine. Teleportation sounds good because it's fantasy. It's science fiction. I appreciate when somebody does like a really good job, a really thoughtful handling of realism, like The Expanse, like The Martian. Yeah, that's great, but it's few and far between. And even those things have all kinds of, like, they have these high power fusion drives. I don't know, are they using metallic hydrogen to fuel them? I don't know. So, like, what matters is a good story. Am I enjoying the story? And I think the childhood Fraser who loved science fiction and loved Star Wars and Star Trek and all that kind of stuff, I feel like he's still here. He's still part of me. And so I will watch science fiction shows and I will be super into them and appreciate just the show and the story and the excitement and the adventure and the cool ideas. And there's a certain kind of book, a certain kind of video game, a certain kind of idea that I've been really enjoying recently. And like, I'm like Mass Effect. If you've like played the Mass Effect game, that is like one of my favorite just themes in sort of space, the future of humanity in space. And then there's the Ian M. Banks Culture series is very similar. There's this kind of like grand sweeping space opera, but sort of dealing with humanity, trying to get along in an uncaring universe. I really enjoy those kinds of books and stories and so on. So no, I find it just as compelling. I mainly still read science fiction, and I'm sure I will forever. Natalie Vincent, how much did the formation and the continued presence of the moon affect the evolution of life on Earth? We're still not sure how important the moon was. I mean, some people say that the presence of our large moon was absolutely critical to the state of evolution of life on Earth. I think also life finds a way. And so who knows, like, if there wasn't the presence of the moon, like how much shenanigans would life have gotten up to without it? But there's a couple of big things. So the first thing is like the presence of the moon causes tides on Earth. And the thought is that you've got this intertidal zone between the ocean and the land. And by having the tide go in and out and in and out, you had life forms that were sitting up in that intertidal zone, and they were able to evolve and sort of sneak their way up toward the land. And that evolution to go from living in the water to living on land was a big one. And it probably wouldn't have been so simple without that tidal effect, allowing, sort of encouraging, giving life an easy way to go from the ocean to the land with evolution. And then the other big thing is that it's believed that the moon stabilizes the Earth's axial tilt. And so we are tilted at a very specific angle towards the sun. We get the seasons. That's great. But potentially without a large moon, the Earth wouldn't have had that same kind of stability. And so we could have had dramatically different axial tilts in the past, which have had big consequences for the climate of the Earth. And in fact, when you look at Mars, there's evidence that Mars used to have a global ocean and that it completely turned itself on its side at some point. And that would have been a problem over long periods of time if there was life there that's trying to get going. And yet, like I said, life finds a way. Life is surprisingly resilient to that kind of stuff. So who knows whether or not the Earth really requires a large moon to have the level of complexity of life that we have here today. And this is one of those things, like people always propose these extensions to the Drake equation. When you think about like, what are the chances there being life, of us finding life out there? And you've got to take the number of planets in the Milky Way times the number of planets that have whatever, right? There's all these numbers. And now people want to add a whole bunch of new things into the Drake equation. But that planet's got to have a large moon, and that planet's got to have a protective magnetosphere. And the planet's got to have a large Jovian planet that is protecting it from asteroid strikes, and on and on and on and on and on. And I think we should give life credit, personally, and just say like when we look at how resilient life is, that we find it deep underground, up in the atmosphere, bottom of the ocean, underneath lakes of ice, snuggled up inside nuclear reactors, in salty environments, in acidic environments. Life seems to be pretty tough. KGS. Are event horizons the most perfect spheres the universe could get? Is there anything to disturb the smoothness or deform them? So event horizons, which is the sort of that dividing line between where light can escape the gravity of a black hole and where it can't escape, is this region around a black hole. Who knows what's inside the event horizon? We can never see it. It's only outside the event horizon that we can actually see this. And event horizons are only a perfect sphere when you assume a non-rotating black hole. So if a black hole doesn't spin, then the event horizon is going to be this perfect sphere. It is a number that falls out of the mass of the black hole. You know the mass of the black hole, you know the size of the event horizon. But black holes spin. They all spin. Many of them are spinning a significant percentage of the speed of light. And what that causes is the event horizon to flatten out, kind of like in the same way that the Earth is an oblate spheroid. Black hole event horizons are oblate spheroids. And so there's this idea of a naked singularity, that the hope is that you get a black hole spinning so quickly that the event horizon would compress down to the point that it would reveal the black hole inside the event horizon. But the reality is that, in fact, this limitation of relativity, that essentially there's a maximum speed that you can have this black hole spinning, always ensures that you can never reveal the singularity. So black hole event horizons flatten out. Now, are they the most perfect oblate spheroids that the universe can produce? Yes, they are. Ronnie Maloney. Is it possible to move from our current universe to the previous one? So the first problem with this question is that we don't know if there was a previous universe. We only know that the universe started 13.8 billion years ago. We see direct evidence in the cosmic microwave background radiation, which is about 380,000 years after the Big Bang. And then earlier than that, we see indirect evidence through the kinds of chemical compositions that are in the universe, as well as our understanding of matter as it is being sort of compressed into ever closer regions. And astronomers can only calculate the sort of the nature of the universe until a fraction of a second after the Big Bang. So we know what the very, very early universe probably looked like, but we can't go beyond there. And it is like a brick wall. It is an impenetrable wall of knowledge that we cannot get past. And so there is likely no information that is available from the previous universe into this universe. So could we get from this universe into the previous one? I can't think of a way that that would happen. However, did we make the journey from the previous universe to this universe is another question. And so, there's various ideas about what the long-term consequences of the universe are. Will the universe tear itself apart with the Big Rip? Will the universe crunch back down with, where the Big Bang will go in reverse and turn into the Big Crunch? It seems like no. It seems like the long-term future of the universe is the heat death, where everything will just move farther away, everything will get colder, and eventually there'll just be no usable energy left in the universe. All neutrons, all matter will decay, maybe even protons will decay after the longest periods of time, and then all the black holes will decay, and all that will be left in the universe is just this soup of particles in this ever-expanding, ever-accelerating universe. But There is one idea, thanks to quantum mechanics, that says that we could live on in some future universe, and that is that you end up with sort of a really slight probability chance that, say, all the air in your room is actually going to be over on Mars. It's very remote, but there's a chance. Now, if you wait long enough, then that chance becomes higher and higher. If you wait billions, trillions, quadrillions of years. And so you can imagine some future universe where more and more random events will happen. And so one of those random events, like it's not zero, but if you sort of calculate the numbers, that you could get a whole other universe just appear inside our universe, that all of matter in the observable universe as we see it today could reform into a new universe, and you get another Big Bang. And so your quantum state could be reformed to this new universe. So there's no way to move from this universe to the previous one, but there might be a way to move from this one to the next one. And so maybe you are from the previous one as well. I don't know. It gets pretty complicated. D-suits. Why can't dark matter be objects? So when dark matter was first discovered, I think back in the 1930s, when they did the rotation curves of galaxies and realized these galaxies should be tearing themselves apart, they're spinning too quickly, they said, well, there's got to be more that we can't see. And then three main theories were proposed. One is that dark matter is some kind of particle that we can't see, like the neutrino. Like we have examples of particles that we just barely are able to detect. The neutrino is a perfect example. Or it could be stuff. So in other words, it could be planets or black holes or all kinds of stuff. Or it could be that we don't understand how gravity works. And in fact, gravity at the largest scales is able to hold the galaxy together. And so since then, astronomers have been trying to figure out which of those three ideas. Is it an invisible particle? Is it stuff, objects? Or is it that we don't understand gravity? And they've been trying to work out those, which of those is most likely. And the one that has fallen the farthest behind is that dark matter is objects, that it's stuff. And part of the problem is just like, as astronomers do more and more observations of the universe, this stuff would be floating in front of other stuff. So you get gravitational lensing. You would see planets, black holes of varying sizes passing in front of stars or other planets, and they would be warping their perspective. And so astronomers have been able to rule out these objects. Now, there could still be about 20% of the universe that is objects. And that could explain dark matter. Like you could have 20% of dark matter is things, rogue planets, black holes, other stuff. And then 80% is some kind of invisible particle, or it could be 10 different kinds of invisible particles. But yeah, astronomers have been able to mostly rule out that stuff, regular matter that we just, isn't illuminated, is not part of dark matter. So we're left with it's an invisible particle, or that only interacts through gravity, or it is that we don't understand gravity at the largest scales. Both of those are still acceptable mainstream explanations for the dark matter observations. All right, those are all the questions that we had this week. Thank you everyone who asked questions, both in the YouTube comments and everybody who joined me for the live show. We do this show every Monday at 5 p.m. Pacific time here on the YouTube channel. It's great. We get hundreds of people show up. They ask questions in the chat. I answer them. We stick around for like an extra hour for overtime. So if you have time on a Monday evening or morning, depending on where you are in the world, definitely come and join us. And I'll put a reminder somewhere here on the channel. And the best thing to do, subscribe to the channel and then click the notification bell, and then you'll get an announcement in your email, as well as a permanent link to the live show. So definitely come and check that out. All right, we'll see you next week. I'm going to talk about the three-body problem show in a second, but first I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Antonio Lofilara, David Giltanan, Dougie Stewart, Dustin Cable, George, Hey Twyla, Jeremy Mattern, Jordan Young, Josh Schultz, Mark Ansis, Paul Rohrbach, Stephen Krasaki, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other patrons. All your support means the universe to us. So I've had a bunch of people sending me links to the new three-body problem trailer that's coming on Netflix. And I gotta say, I'm pretty excited. I read the books. I haven't read them in the original Chinese yet. I'm planning to do that soon. I think I'm ready. But I also watched the Three Body Problem show that aired in China. And it is like page for page, word for word, a complete, just perfect adaptation of the first book. And apparently it was a gigantic hit in China. And so hopefully we're going to see the second book and the third book, which would be great because the second book is a lot weirder and a lot better and a lot more kind of mind-bending concepts. And then the third book is even weirder. And I'm not sure if they have budget for this, but you know, if you saw the ship scene, they've got some budget. So I'm really looking forward to the Western version of the Three Body Problem. You know, there was a lot of problems in my mind with the Chinese version, but still, it was sort of like a pretty amazing version of a book, and the special effects were great. So if you haven't already, you can watch the Chinese version on YouTube. And it's like there's English subtitles. You can just watch the whole thing. It's like 40 episodes. It goes on forever. So buckle up. It takes a while. And that will get you prepared and ready for the Netflix version of it. So there's a lot of good stuff coming on TV shortly. All right. Let me know what you thought of both the Chinese version, eventually the Netflix version, or if you read the book or in the original Chinese. I'd love to hear what you thought. All right. We'll see you next week.